Okay, go ahead. All right. Okay. All right. Okay, guys. Yeah, we can get started. So, yeah, so I just wanted to go over the full, like, kind of the FinFET flow with you and also talk about, a lot of discussions we had in class also. Professor didn't go very much into details. He just gave an overview of what the FinFET looks like, but I thought I would go over more details of the process. And also, I'll upload this video so you can have a look at it when you do your own process as well. And always remember that, whatever I describe here, it's not set in stone. So it's not the only way you can build a FinFET. And I want you to kind of explore different ways you can try to build the device in Cointer, okay? So actually, just a little like kind of history here, right? This was like one of the very first FinFETs that was made. This was by IBM actually. This is like long back, okay? And this was actually one of the first patents. This is from Chen Meng Hu's group. So this was the very first patent that describes how to make basically a three-dimensional transistor, which has this fin and then a gate-like structure, okay? So I think some of the things, about Moore's law. So you started with this kind of bulk MOS where you have like basically a gate region, sidewall spacer, and source drain. But then, as the technology advances, when you hit 45 nanometer, you no longer can use a poly gate. You had to go to a metal gate, basically a high K with a metal gate. And in order to do that, you need to do something called as replacement gate. So you first create the poly sidewall spacer in the original case. But in this case, what you do in the final step, you remove that poly and then you replace it with a high K dielectric as well as a metal. And then you do a polish step to fill in the gate region. That's why if you see when going from something like from this technology to this technology, you see suddenly you get like a very different kind of a cross section, right? With the oxide going all the way around because this is a replacement gate process. And then once you went further and further, this no longer holds. It's difficult to scale a structure like this. And so the only way that you can continue Moore's law scaling and get performance out of the transistor is to increase the width of the transistor, but you don't effectively increase the area of the transistor. So the only way to do that is to go vertically up. So that's where you end up having these fin-like structures. And as you go even further, you go 7 nanometer, 4 nanometer, and so on with the development of EUV, now it's possible to even build more exotic structures like I'm sure you've heard of the gate all around. And in this case, basically like what it means is like, this is a silicon and the gate actually goes all around basically the channel. So here you have the channel going all around the silicon. So you even maximize with even further than what you could do with the FinFET, okay? So, and please ask questions at any step. And so, yeah, so basically this is a structure. I hope most of you understand the difference between
Sorry, about the previous slide. So for the only advantage I have understood about the benefit of the sidewall spacer is acting as a mask for further step. So for example, in the first technology, what's the advantage?
No, sidewall spacer was not meant to create a fin. The main reason for, you mean to create the lightly doped drain region, right? Yeah. That's what you asked.
Yeah.
So it serves multiple purposes, okay? So if this is the gate and this is the sidewall spacer, so one purpose of this is to actually create basically this kind of profile, correct? The only way to make this profile is using a sidewall spacer because initially you do a shallow implant and then you put a sidewall spacer and then the sidewall spacer basically shadows this region so that when you do the next implant, you can get this kind of profile, right? The second important use of the sidewall spacer is when you do the self-aligned silicide process, the salicide process, right? You are depositing metal everywhere over here, and then you are heating it, right? That's how you do the self-aligned silicide. So this region, silicon is exposed, this region, silicon is exposed, and here in the drain also the silicon is exposed, and then you deposit like titanium or nickel, and then when you heat, what happens is the titanium nickel alloys with the silicon, and you get silicide here, here, and here, right? So this is another place where the sidewall spacer is useful because it prevents the silicide from forming in the side. Otherwise, this will short out the source and drain, right? Sorry, the source and the gate, right? So the sidewall spacer has two benefits, okay? And also, another benefit of the sidewall spacer, which is what is used in the FinFET, is the sidewall spacer itself is used as a hard mask to make the fin. So it has many important benefits, right? So, yeah. So basically, so I hope you understood the structure of the FinFET. So the FinFET is quite different from the bulk case, because in the bulk case, actually the gate, the source drain, everything is in plane. But here, actually, the channel, basically the region that conducts the current is like kind of coming out from the surface, and the gate basically wraps around it. And the channel is basically located in 3 different regions, right? So the vertical, the horizontal region here, and then there's another vertical behind it, right? And so how do you increase the width of this kind of fin? So each fin has a certain specific, depending on the technology, a certain specific height and a width. But if you want to go from, say, a transistor 1 width to a larger width because you want to supply more current, then all you do is you just increase the number of fins. Okay, so each fin here is the same size, but then you have a large number of fins in parallel. Okay, and the same gate wraps around all the fins. And now, basically, if you want to know the width of this transistor, right? So the width of this transistor is basically you have to add, you have to go this way, up, and so on, right? So that whole thing is the width of the transistor, correct? And the length of the gate itself is just going to be this, because this is the place where you actually have the channel that is formed, the inversion layer formed, and then the transistor begins conducting, right? And so if you look at, like, here's a typical, like, kind of, these are called, has everyone heard of this thing called as standard cell? So whenever you go to any technology, right, it's like 14 nanometer, 7 nanometer, something like that, any kind of transistor node, what happens is the foundry itself, they come up with certain standard designs which are there in the PDK, right, the process design kit, that you can just kind of, there's a library of it. And so if you're a designer, you don't have to design the inverter every time. So you can just take that thing from the library and you can use it as part of your design. And they're called standard cells, right? So in this particular 14 nanometer, these are some standard cells. This is the inverter X1, which means it's an inverter with a width of one unit, okay? Which means it just has one fin. And there's an inverter with 2, which means it has twice the width, so it has 2 fins, right? So where's the second? Yeah, so it has 2 fins, you see? So this is the fin and this is the gate, right? So here there's only one fin for the PMOS and NMOS, and here there's 2 fins because it's twice the width. And then 4 times you have 4 fins and so on, right? And so if you want to understand how this layout actually works is, so this is the actual fin, which carries the current, which basically has the channel. And this is the gate. And so if you remember the inverter layout, right? So you have basically an NMOS in the bottom, a PMOS in the top, and then you have this metal connecting down to the, basically one of the terminals of the PMOS, and then the current goes this way, and then it is basically sent to the NMOS, correct? And then the gates for the PMOS and NMOS are shorted, if you remember the topology of the inverter, right? And this is the gate. And you have some metal line here that connects to the gate. So if you were to actually operate this device, then what happens is the input signal goes into here, and the output basically comes out from here, right? Yeah.
It's like the source part of like PMOS.
No, see this is the source and drain of the transistors, right? This is a metal line. So how do you go down? So you have to go all the way down to the transistor, right? From the top.
We're connecting VDD to that.
Yeah, this is the VDD. So this is the VDD, right? So this is one metal line that carries a VDD. There will be a VR here that goes to this metal line. And from here, there's a contact that then goes to the source in this case. And then similarly, you have another metal that takes it out from here, brings it here, and then goes down again, and then so on, right? This is just a top view. It's a 2-dimensional view, but this actual structure is 3-dimensional. There's like, basically there are like multiple levels, right? And to go from one level to another, you have vias or contacts, right? Yeah.
How do you form the trench oxide?
The trench oxide, what do you mean?
How do you make it recess so the thing is like standing?
I will talk about the process. Yeah. Yeah.
Why would you choose the 2-fin or the 4-fin over the 1-fin?
Oh, so basically it depends on how much current you need to supply. Okay, the way it works is like, usually when you're building a digital circuit, right? You have the inverter, and the inverter is basically whatever you input to it. If it's a 1, the output is 0, or 0, the output is 1, right? And then that has to go to the next stage. So there will be some other circuit after that, right? So you can model that circuit in the second stage as just a capacitor. So what the inverter does is basically charging or discharging a capacitor at the output. Okay, so what I mean is like, So this, if you look at the circuit, right? So this is just, this inverter is just like a PMOS and an NMOS. And this is the input. And then the output then goes to some other stage, right? But the entire stage can just be modeled as some capacitor. Okay. So what actually it's doing is either it is charging this capacitor to this supply or it is discharging the capacitor to ground, right? And the speed at which it can charge or discharge this capacitor depends on how much current is going through this transistor, right? So generally, if the transistor is wider, it can supply a much higher current. So if you use an inverter which is twice the width, it will be twice as fast, for example, because it can carry twice as much current. So it can charge and discharge the capacitor twice as faster.
So twice the width is like 2 times 1 fin width.
Yeah, because 2 fins means twice the width, right? And why, you may ask, like, why sometimes use in smaller inverter? So it really depends on your circuit. Like sometimes you care more about the area, or there's also like optimization. Sometimes using a 1 width transistor is more optimal and so on, because you have to optimize area, power, as well as speed. Okay, so when you do that optimization, right, you have certain sizing for all the gates and all that. So that's why you have all these options.
Now the gate is polymer.
Hmm?
Now the gate's material is polymer.
No. There's no poly here. It's all metal. I'll talk about it. There's no poly. Yeah.
The width of each fin is the vertical plus the horizontal plus the vertical.
Yeah, because see this, so basically the width is going to be, the width is basically the part that is conducting the carriers, right? It's basically the inversion layer, right? So where all is the inversion layer forming? It's forming vertically here. It's also forming horizontally on the top, right? Some cases, the fin, the top one, there's no inversion channel because it kind of tapers off at the top. So you don't really have much space at the top for inversion layer. So, but if whichever region actually has the channel, that contributes to the width, right? So in this case, it would be basically, if this is basically a rectangle, right? So it will be the 3 sides of this rectangle. So you add the length here, plus this length, plus this length, and so on. That's the width of the transistor. And so, like you can have very complicated layouts, but obviously we're not going into it, depending on what your gate topology is, right? And when you build a chip, you have basically a whole bunch of these on the chip. But again, no one does this by hand. There's usually software that automatically generates all this. But in our case, we're particularly talking about this, okay? So even your layout for this particular process is going to look something approximately like this. There will be other masks also for the implant and all that, which I will talk about next. So next, okay. So now let's actually talk about the process, okay? So I hope you guys follow along and then ask questions any step that's like, not able to follow, okay? So first you start with basically your silicon, right? And then you put a pad oxide, pad nitride, and then you put your polysilicon on top, okay? The purpose of this polysilicon is it acts, yeah.
So how do you define the lateral dimensions of the wafer, the base wafer?
No, okay. Try to understand the process now. The software related issues we'll talk about later, okay? Because there's a lot of steps. I want to finish it and then we can discuss the software issues. But if any questions respect to the process, you can ask. So it's silicon, pad oxide, nitride, and then there's polysilicon, right? But this polysilicon is a mandrel. It's going to act as basically the mold for creating your fins, okay? Yeah. And so the next step is, you need to define your polysilicon mandrel, right? So for that, you have to pattern this. So you need a tri-layer resist, right? So you need the ODL, you remember the optical planarization layers, then anti-reflection coating, and then a resist, right? And then on top of this, you basically do your lithography, right? This is the first mask for defining your mandrel, right? So you use the mask here, you pattern this resist, and then what you do is you use this resist to pattern basically your different layers, right? So first you pattern your psi arc, and then you use your psi arc to pattern your ODL, your planarization, right? So remember, when you do this patterning, you do one step at a time. So you use one to pattern the other, and the other, and the other, and so on, right? So that's what's done here. And then finally, you see the pattern is transferred to the poly, right? So this poly is now the mandrel, okay?
Oh, sorry, can you go back one and then look to this again?
Yeah, I just patterned this, that's all. I just used basically a 3 layers.
Transfer it, you're removing the top, and then, no, you're etching first. And then
Yeah, so first I patterned the psi arc, then I patterned the planarization layer, then I use this to pattern the poly, right? And patterning is done by dry etching, RIE. So now you have this pattern band, right? Then what you do is now you define your sidewall spacer. So remember how you create the sidewall spacers? First you do a CVD. Yeah.
I remember you said you usually do the dummy fins. Are you just not doing them for simplicity of the?
No, this is the dummy fin.
Oh, this is.
Oh, the dummy fin. No, yeah, the dummy fin I haven't shown here. Yeah.
Are we supposed to do the dummy fins?
No, you don't need to do that. Yeah, but you just need to know that when you do this in reality, right? You have a lot of dummy structures for the diffractive effects. But here, no. Yeah, so next is, yeah, you create your sidewall spacer, right? So how do you do it? You first deposit conformally an oxide, and then you etch vertically down, and what happens is the sides don't etch, right? So as much, so that you end up with this kind of sidewall spacer here. And then after this, what you do, you basically remove, yeah, okay, now this is important, right? So does everyone remember the concept of the cut mask that we talked about in class, right? So when you define this poly, remember this is like on a wafer. So when you actually define this poly, right? So when I actually pattern this polysilicon, yeah, it has some dimension here also, right? Although I showed only the region here, I showed only this region, but at some location somewhere here, it has an end, right? So when I create the sidewall space is located all around, right? But I want my fins only here and here. I don't want my fins here, right? So you have to open up a mask and remove the oxide, the sidewall spacer here, so that you don't have a fin at that region. Yeah.
Are we supposed to actually do this, like with the making it in 3D and usually cut mask in Codentor? Is that just?
Yeah, that's what I've done. Yeah. So you need to remove it at regions where you don't want the fin, right? So that's why you see this is a sidewall spacer, but I want to cut the sidewall spacer. So basically, I'm showing this region I'm cutting, right?
That's
So
not in plane. That's not in this, right?
it is going to be shown.
Oh, okay.
I'm going to remove some region of the sidewall space.
But this is already removed.
No. This is just a portion of the simulation.
Oh, okay.
I haven't removed it. You can't simulate the entire wafer, right?
Yeah.
You're simulating one region,
Right.
right? But I'm just showing you the concept of how you can do the process. You only care about how to do the process, right? You don't you're not actually building something here. Yeah. So basically, this is the cut mask. So you put resist and you cut this region, right? And so in this region, you have opened up over here, and you're going to now remove the sidewall spacer, correct? So now you see sidewall spacer is etched. And so now you have only sidewall spacer here, and some region here was removed where you didn't want it anymore, correct? And then now you remove the polysilicon, right? So now you see here, you're left with these two freestanding sidewall spacers, and some region of it has been cut, okay? Now, exactly why it's cut here is just to show you that how to do it, but it just, you just want it removed at the region where you don't want to fit, okay? It can be at any region, doesn't matter.
How do you remove the polysilicon?
This is etching.
Don't etch the oxide?
No, because you always, so when you etch, any etching you do, right? What are the things you etch? You etch organics, you etch oxides, you etch nitrides, you etch silicon and polysilicon, right? You can always select an etch that etches one versus the other. So you can etch poly, but you don't etch oxide or nitride, right? Because there's nitride in the bottom and there's oxide here. If I use a poly etch, it's going to only etch the poly. It's not going to etch anything else around, right? So that's why the polysilicon is now etched. And then you just have this oxide sidewall spacer is freestanding, right? And now what you now use this oxide sidewall spacer as now the hard mask to pattern the nitride and the pad oxide. And then you use this to then act as the mask to etch down the fin, right? So now you have a silicon fin that you see, there are two fins here, right? And what's going to happen is this fin here is going to be actually your NMOS, and this fin here is actually going to be your PMOS. Okay. Yeah.
That was like 3 to 4 etch steps that you just did, right? You did the nitride, pad oxide, and silicon.
Yeah. There'll be 3 different etches.
There's
Yeah.
3 different etches.
Yeah. Because oxide will be one etch, nitride will be one etch, then again, silicon will be another etch. Yeah. So now you have etched down and you created, and this fin is going to be for your NMOS device, that fin is going to be for your PMOS device. Okay. Yeah.
CMP here, so what? Yeah.
There's no CMP here so far.
No, but so far you have not done any CMP.
No.
So why did you need the nitrogen?
Oh, because it's needed later on. I'm thinking ahead, right?
Okay.
Yeah, it's not, as of now, it's not used, but it will be used soon, very soon, actually. Yeah.
To use a sidewall spacer to define the fin, you can't just use photolithography.
No, yeah, someone else also asked me, see, most of these FinFETs were created at a time when EUV didn't exist, right? So with the more primitive lithographic techniques, you can't get like sub 20 nanometer features with lithography, right? It's difficult to do. That's why you use sidewall spacers to do it.
What about for?
No, you do it through sidewall spacer process. For 14 nanometer, it's still done with sidewall spacers. Yeah. Yeah.
So in this example, from one mandrel, you make both the FinFET and PFET. When we make our layout, and we use like two mandrels.
So it'll also be different from this. This is just demonstration of how the process, right? But you're obviously, yeah, in your case, it'll be different. But this is how you would do it, you know. So now that you have, yeah, so now that you have, and this region of the fin that you've etched, okay, this is like, usually what you do is you will like etch it, but then just remember that whenever you do an etch, you'll also do a treatment, okay? You'll do actually like kind of like a thermal oxidation as well as wet etching of the oxide because you want to remove damage from the site. Okay, it's not shown here, but you do that.
That's for actually silicon.
Yeah, yeah.
So for the pad oxide.
No, those don't carry the current, right? You only care about only in the cases that has the current. So then, yeah, so this is the active region of the fin, but you also want to kind of separate them out. You want to isolate them, right? So then you have to create your basically a shallow trench isolation. So you continue this fin etching process, but this first etch is actually a very anisotropic etch, so it etches vertically like this. And then you do a more tapered etch here to define this. You go deeper, okay? So it creates this, and if you see here, that's how these technologies are. So initially there's this anisotropic etch, and then they do a more wider kind of tapered etch. Yeah.
Do you do your treatment after both etches have been done, or?
No, once the silicon is etched, you do your treatment.
So the first initial anisotropic etch.
That time you do treatment.
That tapered etch.
Yeah. No, tapered etch doesn't need treatment.
Doesn't it fill with oxide?
I mean, you can do, yeah, but you see, this region is not going to conduct current. You only care about the region that's going to conduct current, right? This is the region that's conducting current.
Okay.
Right. This is just for the isolation, right? And it also has a mechanical stability, actually. And then, like, so yeah, so then you do this basically this tapered etch, and now you need to fill everything with the oxide, right? So that's where the CMP step comes. So once you made your full fin, then what you do is, oh yeah, before that. So now you have the N fin, so basically the NMOS fin and the PMOS fin, right? So now the question is, how are you going to dope this, right? So there are multiple ways to dope it. One way is to actually do ion implantation and diffusion, okay? But I have done it actually with basically a different way using polysilicon itself to dope the silicon, okay? So remember, right, in a transistor, in the case of the NMOS, feeling none of this. Yeah, so remember that in the case of the NMOS, right? This was the NMOS. So you have basically the source and drains would be N type, so it'd be N plus, N minus, N minus, N plus. And this, the well itself, right? So this is called the well, the region of the body. And this will be P type, right? And then you have oxide, and then you have some metal, right? So this is the structure for your NMOS, correct? And the PMOS would be opposite to this. So PMOS would have P plus, P minus, and the body would be P type, right? Sorry, N type. So let me just write that so it doesn't create confusion. For the PMOS, it'll be exactly opposite. P minus. And then type loud. So basically you want to create these. So now you have the fin, right? Remember, in the FinFET case, this body is actually the fin itself, right? So you need to uniformly dope the fin to the doping of the body, right? So this body is P type here, which means for the N fin, so the NMOS fin has to be P-type doped, and the PMOS fin has to be N-type doped, correct? So how do you do that? So I'm actually going to do that with polysilicon, with doped polysilicon, I'm going to dope the fin, okay? And how you do that is what you can do is like, if say you have silicon, right? And you want to dope the silicon, say N-type, what you can do is you can actually deposit on top of the silicon. So usually there will be some layer here, which is basically called as a diffusion barrier, which is usually made with some kind of a thin layer of oxide, okay? And what it does, that's to control the diffusion. And then you can put N plus poly or some highly doped polysilicon. And what happens is when you anneal this, the N dopants actually migrate into the silicon, okay? And they end up creating a well, which is N-type here. And then you can remove the poly, okay? So that's one way you can, this is using diffusion to dope the silicon, but you can also use ion implantation to dope the silicon, okay? So that's why I'm saying this is one way to do it, okay? So what I need to do is I need to create a P well for the NMOS and an N well for the PMOS, right? So what I'm going to do is first I'm going to deposit, so this region is actually this diffusion barrier over here, diffusion control barrier. So that's to control the amount of diffusion. And then I first deposited a P, basically I've deposited a P-doped polysilicon, right? And this P-doped polysilicon, remember that NMOS is the one that has a P body, right? So I need to have this only on the NMOS and I need to remove it from the PMOS, correct? So that's what I'm going to do in the next step, is I'm going to basically pattern. So I put a resist, pattern the resist. And then what I'm doing is I'm etching the polysilicon from the PMOS side, right? So now I have this P poly sitting here and no polysilicon over here, right? Then after this, what I'm going to do is I'm going to deposit another polysilicon that's covering everything, but this is going to be N polysilicon, right? So now you have N polysilicon on the PMOS and P polysilicon on the NMOS, correct? There is N polysilicon on top of this P polysilicon, but that's far away from the silicon surface, so you don't really care about it. I knew you would ask that question. Yeah. So basically, you know, the P fin, right, is touching the N polysilicon and the N fin is touching the P polysilicon. And so now when you anneal this, they're going to basically diffuse into it and they're going to dope the fins, right?
They diffuse at the same time.
Yeah, because I'm annealing it together. What do you mean mobility will be? If the mobility is different, I just dope these polys different. Yeah. So also, you know, in some cases, right, you don't want these nitrides and oxides to also be filled with dopants. You don't want to make this conductive. So what you do is you also etch away the polysilicon on the top, the tips of this. And so you have polysilicon only on the sides, okay? So that you can do with the same kind of etch you use to create a sidewall spacer. If you do that, you end up etching the poly so that they are only located at the sides of the fin, okay? And then now when you do the drive-in, right, the thermal anneal, so this becomes doped P-type and this fin becomes doped N-type, okay? So everyone understood up to this point, right?
Just so I'm still on track, we have had 3 masks so far, right?
I didn't keep count of them, but yeah, I'm taking your word for it. Yes. Yeah. So there's also alternate, yeah.
Smaller because of the difference.
It's not smaller.
Like length. Or did you do that just to show how cut mask works?
No, they are the same width here.
You're saying the cut mask.
Oh, that's just to show you can cut it. Yeah, yeah. It's just to show you can, yeah.
That's just.
Yeah, that's to control because if you put poly, first of all, you don't want to put polysilicon directly on silicon because it tends to like kind of contaminate the silicon because it has like grain boundaries and all. So you always put some, but there's a thin barrier layer. All it does is it kind of controls the amount of diffusion you have.
That's oxide.
Yeah, it cannot be a nitride, but it can be an oxide, a thin oxide. And like, you know, it basically serves the same purpose as the implant screening oxide you use, right? That's used to control how much of the implant, how deep it goes in, right? It serves the same purpose here. It's basically to control how deep the implants go, right? Yeah. And so, you know, I hope everyone understood that, you know, now this fin is fully doped P-type and this fin is fully doped N-type, okay? And the value of the doping that you need to calculate based on how much threshold voltage you want, right? The same way you calculate for this. Yeah,
If we were to use ion implantation.
that's the next thing. So there's an alternative way to do it. If remember here, because you're using diffusion, right? It's gonna kind of dope this uniformly all the way around, right? But if you're doing ion implantation, so remember ion implantation is directional, right? You're gonna shoot it at one direction. And so when you have this kind of fin-like structure, if you're doing ion implant from the top, then it'll end up heavily doping this region, but lightly doping this region, right? So usually what people do is typically you don't care much about this region. You only care about the doping of doping of this region, the sides. So typically what people do is they dope it at an angle. Okay, so they implant once on this angle and then the other one at the other angle, right? So typically, they do it like, for example, this is done at 30 degrees, right? So 30-degree this side and then 30-degree that side to do the implant on both sides of the fin, right? And remember that when you do one fin, right? So in this case, say they have doped this particular fin is N-type dope, which means the P fin. You have to make sure you cover the N fin, right? Otherwise, these should not be doped. And then vice versa, so that you can get the, each fin gets the corresponding doping you want, right? So this is how you do it with ion implantation. Yeah, so let's continue. So yeah, so now everything, the body is doped, and then you have this oxide. So now comes your CMP process, right? That's why I put the nitride in the beginning. So now what you need to do is you need to fill all the space with oxide. That's your trench isolation, right? So what you do is you do this CVD deposition, a PCVD of this high density plasma oxide. So usually when it says HDP, so there are so many different kinds of oxides you see. Okay, there's TEOS, then there's like LPCVD oxide, and there's HDP oxide. So HDP means high density plasma oxide. So HDP oxides are typically very dense. They don't have as many, how dense an oxide is determined by usually oxide is SiO2, right? But usually it's not SiO2, it's SiOX, and can have some oxide vacancies in it, right? So the HDP oxide is one that's almost like SiO2. So it's like very dense oxide, it's a good quality oxide. But actually, when you go higher and higher, when you go to a metal 1 and metal 2 and stuff like that, you actually use a poorer oxide, okay? Because it actually helps with your dielectric constant, because the good oxide actually has a higher dielectric constant than the more porous oxide. So this is a high density plasma oxide, it's an HDP oxide, and now you need to like fill everything in, right? So that's where you do the CMP. And the CMP obviously stops on the nitride we had in the beginning, right? So, and then you also have some dishing here. And then now what you need to do, you need to remove these hard masks, right? You don't want this nitride oxide. So what you do a little recess etch of this HDP oxide, and then you basically, and this step is usually called as deglazing. And then what you do is you wet etch the nitride, okay? Yeah.
Why did you deposit so much height?
So much height of oxide.
There's like 3 fins of height of oxide. When you did your
Why this oxide is over here?
No, the HTP works oxide.
No, that's because see, the thing is, it's just to show. It doesn't really matter. I could have done till here also. Yeah. Don't worry about how much I use in the dimensions.
The numbers don't matter.
Yeah, it's just the process is what I want. Yeah.
Why do you make this tall?
Which the fin?
The fin is the top region of this whole.
So the part of the fin that's actually used in the conduction is only this part, okay? So this part is actually meant for, there are some electronic reasons they make it wider at the bottom. This is a mechanical reason why they make it like that. There's also an electronic reason why they make it like that.
For thermal dissipation.
No, it's not because of thermal dissipation. Thermal dissipation is worse when you make it taller, actually. It's to do actually with like mechanical stability and as well as the electrostatics of the device itself. That has to do with why it's built. Yeah.
Why did we not remove the diffusion barrier?
It is removed. Yeah.
That blue part is.
Oh yeah, I forgot to, but it's removed.
What is the research step for this? You said something.
Recess etch.
Yeah.
This is recess. No, recess just means, what is the meaning of recess? Recess just means this, you're etching this down and then this goes some depth down. That's called recess. Yeah.
How are you doing the recess edge? Is it just isotropical edge?
No, it's just a dry etch. But you see, if you dry etch an oxide, right, the nitride is not going to etch, right? So the nitride behaves as a mask. And then everywhere the oxide is there, it's just going to etch down.
In order to get that depth, is it just like fine tuning and?
Yeah. It's just process. So usually also, right, when you tend to etch something, right? So imagine you had like something like this. That's how deglazing works. So if you have some feature like this, right? This is say oxide. So usually when you do a blanket etch, when you etch down, right? The things that are sharper tend to etch slightly faster than the things that are like this. So this ends up, like say this had some amplitude, right? This basically this roughness had some amplitude. And when you do this kind of dry etch down, this amplitude reduces actually, because the sharper places tend to etch slightly faster. That's why here, if you see here, like when you do this deglazing step, right here, the slope was higher, right? But here it's like not as high, right? Yeah.
I remember when we did like STI class, we did ALD and then we positive oxide.
That's all there. I haven't shown it here.
Okay.
Yeah.
In reality, how do we control the recess edge that it stops at the?
How you do it in practice?
Yeah.
You do DOE, like design and experiment. You do like multiple runs, different etching times, and then you see you do. So basically, if you're doing this in industry, right? So you first do different etch rates, different etch times, different etch energies, and so on. And then every time you do, you take a cross section of the device, you do a fib, and then you do an SEM to see how this profile looks like, right? That's how you do it. That's why, when you go to process engineering places, right, you have one engineer working on one process. They're called unit process engineers. So one engineer's entire life is just oxide etching, right? So no one knows the guy who puts everything together is called a process integration engineer. Okay. He's the one who like says, I want, this is a structure, this is what I want, right? But each individual process is done by unit process engineers whose sole job is to work on developing this process. And then you have someone else called as a tool engineer whose only job is to make sure the tool gives you what you want, right? So like, yeah.
For the identification process, when you're doping one side, you cover the other side. Like what material do you use to kind of?
Oh, it can be either you can use resist or you can use some thick hard, because see the resist you need much higher thickness, right? To prevent the implant from going in. Otherwise, you can just use a thick oxide and nitride to prevent the implant from going in. Yeah. Yeah. So after that, you did basically the deglazing and you have the surface. And then you remember now you have to actually expose your fin, right? Because now you want to build the gate structure and all that. So now what you do is you basically, you remember this is silicon and it's surrounded by oxide. So now if you do an oxide etch, right, the silicon is going to stand up, but the oxide around it is going to recess down, right? So now if I do another recess etch, so I get the silicon now exposed on the top and all the oxide around it has kind of gone, right? So this becomes the fin that's actually going to be used for now making your transistor. Correct. Yeah. Okay. So yeah. So next, so Narendran, so 40 minutes is up. So will it automatically stop or will it tell you it stopped? Okay, then.
Actually, Zoom will end.
Huh?
40 minutes if there is no.
Oh, yeah, then let's just continue. Yeah.
No, it will end, right? You won't get the recording.
No, but it'll tell me the recording stopped, right? Huh?
Nice.
Oh, okay. Yeah. So so now you made the fin, and now the next step is how to actually make your gates, right? So now you have the actual region that conducts the current. And now you actually want to create a gate on top of this, right? That's perpendicular to the channel, right? So how do you make that? So far, this is what we've done. So if you look at the typical cross section at this stage of the process, so it looks something like this, right? Yeah. So next, you put some, remember always when you have silicon exposed, right? You never want silicon to be exposed. Okay. It's not a good idea. So you always protect it with some barriers. So in this case, it's some oxide, some ALD oxide barrier. And then now that you have this, then what you do now, you're going to create your actual replacement gate process, right? So I hope you guys, so to do this, right? So the first polysilicon you use was the mandrel to create the fins. The second polysilicon you're going to use is also not going to be used eventually. It's going to be replaced with metal, right? So the replacement gate process, if you remember, is you use the where was the one I just used? That's the one I used. So, the replacement gate process is basically you first have poly, and then you create a shallow implant, and then you made, your sidewall spacer, then you made the deep implant, right? And then once you made this structure, right? There's also, you also need to add strain engineering also. We'll talk about that. But then in the replacement process, what you do is after you've done everything, you remove this polysilicon, right? So you have this removed. And then what you do is you fill this up with metal, right? You first deposit some high K dielectric here, and then you fill this up with metal, right? So the polysilicon is finally removed, right? So we're going to do that over here.
So before that, you have another alignment, right? You have the metal right.
No, this is also self-aligned.
Okay.
Yeah.
So you will deposit metal everywhere.
Oh, you mean, no, when you define your first gate, right? This polysilicon gate. To define the polysilicon gate, yes, there's a litho step. But then to do replacement metal, there's no litho step because the replacement metal is just going where the polysilicon was originally defined, right?
Oh.
Yeah, I'll talk about that. But what you'll do is like, say this was polysilicon first, right? So what you do is you kind of fill some kind of oxide and then you CMP down. So the oxide is like over here like this. Then you etch away your polysilicon. And then you sputter like you do an ALD hafnia and then metal, and then you CMP down. And then it's filled only here, right? And then everywhere else goes away. But you don't need a mask to do that because it's just defined in the place where your polysilicon was originally present, right? So that's the replacement gate process. Yeah. So yeah, so now this polysilicon is for that process. So what do you do? We first deposit this polysilicon and we planarize it. So we do a CMP, but this CMP does not need a polystop. Okay, it's a reference CMP, which means you CMP for a certain period of time till it gives you some thickness, and then you stop. And the way you do this in practice is you do CMP for different times, and you do a DOE, and you find out which gives you the right thickness you want. And now you need to pattern this poly, right? You need to define the gate. So to pattern this polysilicon, you have some nitride, some oxide, which is going to be the hard mask to pattern it. And then, to actually transfer the pattern to this, you need to do a litho, right? So therefore, you again do the 3-layer lithography. So it's ODL, SciArc, and resist. And now what you do is you expose the mask and you pattern this, and then now you etch all the way down. And now you transfer the pattern of the gates, right? So of the gates to this planarization layer, and then now you use this to pattern your polysilicon. Right?
What's the material of the gate?
Huh?
The red is the poly, right? What is that, like grayish?
That's the ODL. That's the planar optical. Oh, sorry. No, that's the nitride. That's the nitride.
No,
Green on top?
That's the oxide. This nitride is very important actually, because we need it for the polystop when we do the replacement, right? Yeah, and so now the next step I show it's an optional step, which is usually done because sometimes what happens is in this step you want to create like a uniform mask, and then in the next step you want to cut out the gates at the region where you don't want the gates. The same way I showed for the fins, right? So I first created the fins, and then before I created the fins, I first created the sidewall spacer mask for the fin, and then I cut out those in regions I don't want, right? The same thing is also done for the gates also. So first you define your gates, the hard mask for the gates, but before actually etching the gates down, what you do is you have another cut mask to cut the gates at certain regions you don't want them, okay? So here is an example of a cut mask for the gates. So again, you do a 3-step resist process. So there's a planarization layer, SciArc, resist, and this is the cut mask for cutting the gates, right? So you pattern this, and then you basically transfer the pattern to the ODL, and then you etch this nitride. So now you have cut the gate at certain regions, right? And so now, once the gate is cut, and then you have, this is your gate hard mask, right? So you have the nitride has been patterned and the gate over here has been cut. And now you just transfer this pattern onto the polysilicon. So you just use a silicon etch, the polysilicon etch, and then now you have etched down all the way down. And now these are your polysilicon gates, right? With the nitride on top. Yeah. Next, what you have to do is, so this step is going to get a little complicated, so just follow along, is what you're going to do is, you have to create the same way that in your planar MOSFET, right? Let me remove some. So remember in your planar MOSFET, what you actually do is, once you created your, also, yeah, one more thing I wanted to say is, there is also an implant step for creating the lightly doped drain region that I've not shown here, okay? So that part you have to kind of do it yourself because you need to calculate how much doping is for the lightly doped drain region. But remember that how you create the strain engineering for the bulk MOS, right? So first, what you do is you create a lightly doped region. And then what you do is you kind of create the sidewall spacer. And then you etch the silicon down like this. But you do basically a wet etch. So you do a crystal etch. And then you epitaxially grow your silicon germanium, something like this, right? And the silicon germanium in situ doped. So it's in situ doped to, like, you know, if this is a NMOS, this is in situ doped N plus, right? And this will be N minus. So this, and what happens is this, sorry, if it's, yeah, this will be silicon carbide for the NMOS. And so what this is going to do is going to basically create a tensile stress on the transistor, right? And on the channel, and that's what's going to create your enhancement in the electron mobility. Right? Yeah.
How do you do the sidewall spacer over the fin? Because if you're doing.
Oh, no, we're not doing it over the fin. Remember, that's a slightly confusing thing here. In this case, the fin is going in one direction, the gate is going the other direction, right? The sidewall spacer is created on the gate. The fin sidewall spacer that we created before was to define the fin, but now we are going to create another sidewall spacer, but it's going to be on the gate, on the polysilicon gate.
Okay, so then how would you, it's still gonna be a 3D topology, right?
Yeah.
And so then in that case, how would you do it? Because there's, you're gonna do an anisotropic etch, right?
So say this is the fin, right? So what you're going to do is you're going to put a polysilicon like this, right? So it's going to be something like this. And then on top of this, what you do is you deposit oxide or nitride, and then you etch down, and then it's going to create a sidewall spacer like this. But you see, it's perpendicular now, right?
Yeah.
And yeah, and then you do the same thing. So first you do a lightly doped implant. Yeah.
How do you get on the sides though? Because if you're doing anisotropic etch from the top, right, then it would.
No, anisotropic etch just is from the top, right? It doesn't matter whether it is doing this way or this way. It's still going to create a sidewall spacer.
Okay.
Right? So see, it's a little difficult to draw this because it's three-dimensional, but this is going in this direction, right? This gate is going orthogonal to it. So if I was to draw, it's something like this, right? And then what I'm going to do is I'm going to deposit, but in this orthogonal direction, I'm going to deposit like, yeah. And then the sidewall spacer will come like this. So first you deposit, and then when you vertically etch down, it's going to create the sidewall spacer on the gates.
So the process can change.
No, it's the same, exactly the same process. And you will see that over here, right? Remember, this thing over here was the pins, right? It's the thing that carries the current. And these are the gates, right? So, yeah, so what you do is now you need to create your lightly doped region. So that's why first, that step alone is not shown here, but you would basically create this mask on top. You would open up first the NMOS region, and then you do a lightly doped N region. And then you close the NMOS region, open the PMOS region, and you create a lightly doped P region, right? And so now what you need to do, you need to do this step where you etch the silicon down and then you epitaxially grow your, yeah.
Like, where would the likely doped region be? Like, is it around the whole fin or just like that?
No, so in this case, right? So if this is the fin, right? So your gate is going to go around it like this, right? So it's going to go like this. and then back, correct? So let's say this is the gate, it's going, it's going on top of, I think I drew this somewhere. Yeah. So basically, this is the FinFET, right? So this is the source, right? And this is the gate, correct? It's going on top. So your question is, where is the lightly doped region, right?
Yeah.
So what you do is here you'll have sidewall spaces. So imagine this is
Oh, so it's just like right outside.
yeah. So here there will be a sidewall space that will come like this.
Yeah.
And so first what you do is if you do a lightly doped implant, right? This region will be lightly doped, like over here like this, and this region lightly doped. Then you create sidewall spacer, then you etch this down, and then you grow the silicon germanium here.
But where's our like heavily?
Wait,
the
wait.
other-
No, the silicon germanium is the heavily doped region. See, it's in situ doped.
This one pseudodope means that you grow it and it's doped.
Yeah. So when you grow epitaxially, you add arsenic gas into it, for example, right? And then as it grows itself, it becomes doped.
So there's no reason to do a heavy doping.
No. In this case, you can in situ dope it. Yeah.
So after doing that light doping, we are done with the front of the line. We're now moving to the middle of the line, where we do the singulating.
No, we are still not even close to middle of line.
I thought the singulating was the middle end.
It's middle of line, not middle end of
Sorry,
line.
the middle.
You're either the middle or in the ends, right?
Sig is like the middle, right?
Huh?
We're done defining all of our electric.
No, CE and then no, that's not middle. Oh,
The
you're
student talked about it as middle line.
no, that's front end of line. Okay. Middle of line is to create the contacts to the source drain. So you understand, it's very important to understand three-dimensionally how the FinFET is, right? So in this case, this is the source and drain, and so these regions are going to be now the silicon germanium. And then if I was to draw, right? So if I was to draw the same thing over here, this would be like this, and go like this, and then like this. Understand? In that plane, right? And so this will be lightly doped region, and then this whole piece will be replaced with silicon germanium. That's your N plus, right? Yeah. Okay, let's quickly go through this part. Yeah, I think this is the only part will be a bit confusing because it's a little complicated. Yeah, so basically, you put the oxide and then you put the nitride, and then you have a mask because you want to open one side, because one side you want silicon germanium, the other side you want silicon carbide, correct? Remember, this was the NMOS fin, and the PMOS fin is sitting in the backside, right? So the PMOS fin is going to be silicon germanium, the NMOS fin is going to be silicon carbide.
What is the reason that you cut the gate? Because for example, for the inverter.
No, it's an option. Like, I just want to show that it's an option to cut the gate. You don't have to cut the gate. It's an option, because just like how you can first create a fin and then you cut the fin where you don't want, right? Similarly, because it's mentioned in your PDF document, you have cut mask for the fin, you have cut mask for the gate also. So I want to explain what the cut mask is for. That's why it's, yeah.
So I got a little lost. We did the oxide depth, we did the nitride depth, and now we're doing a silicon germanium growth.
Yeah, see, basically, right, if I was to draw the planar case, right? So say this was the PMOS, this was the NMOS.
I know where it is.
Yeah.
My question is, so when you do the silicon germanium growth, you're already doping it. Whatever heavy you dope.
Yeah.
You're growing it.
Yeah.
And then we cut it, so it's a reductive process. You grow one, cut half, and you grow the other.
No, what do you mean cut?
You're cutting that.
No, I'm not cutting anything. That's what I'm going to explain. Is what you do is, I'll explain in the planar case, right? Because it's easier to draw. Okay. So what I'm doing is I'm covering all this with like some oxide nitride mask, right? And I'm assuming it's already lightly doped. I've not shown that, but you already create the lightly doped region. But now what I'm going to do is I'm going to put mask, okay? And then if I want to create, say, I need to create silicon germanium here and I need silicon carbide here, right? And these are grown epitaxially, right? Which means what? Which means they're put inside some furnace. They're heated to high temperature, right? Which means you cannot do this with an organic. You need some inorganic mask to prevent the silicon carbide, silicon germanium from forming, right? So what you do is you have this mask, this nitride mask, nitride oxide mask everywhere. and then you just open it up in these regions, right? So you open up this region, and then you etch the silicon down like this. Right? Or here. And then this is still covered with nitride, right? And then now when you put this inside the epitaxial growth for the silicon germanium grows here like this. And it is in situ dope, right? In this case, it will be in situ dope P type, right? So it will be P plus dope. And then what you do is then you basically cover this again, and then you open this side, and then here you again etch down, but here you grow silicon carbide, right? So when you grow one, the other one should be covered. That's the main point.
So after we grow our silicon germanium, we cover the left side, then we're gonna open up our right side.
Yeah. And the reason this nitride is there is because you have to use some inorganic to cover it, to mask it. You can't use resist to mask it, okay? Because you can't put resist inside a furnace.
Any reason why you're doing silicon germanium?
That's your choice. Yeah.
Is there like, do we need to like wait a minute between doing any of these steps for something to dry or anything like that?
You mean in practice?
Yeah.
Yeah, I mean, they could be done, yeah, because you would etch it, you would grow it, and then there'll be a lot of cleaning steps in between.
Okay.
Yeah, typically. And also there'll be a lot of etching steps also, because once you create the silicon germanium, right, you need to kind of close this again, and then you need to open this, and then you need to do another wet etch to create this, and then you grow silicon carbide.
Is this purple material?
That's resist, because I need to remove the nitride here, right? To do that, I need a mask. That's why you need that resist. Yeah, so this step, yeah. So basically what I'm doing here, it's hard to see, but I mean, you can't see, but on the other side, I'm growing silicon germanium. So I'm opening up using the mask, I'm etching down the silicon and growing silicon germanium. But you can see for the silicon carbide, actually. So now again, I'm covering with nitride. Remember what I mentioned, right? So now I'm going to open the silicon carbide region. So this one you can see. So again, I put resist, pattern the resist, right? And then what I'm going to do is I have etched the nitride all the way down to expose the silicon on top of the fin. And then what I'm going to do, I'm going to crystal etch the fin, right? So that's what I've done here. So I've crystal etched the fin down, see here. And then now I'm going to epitaxially grow the silicon carbide, right? So you see here the silicon carbide is grown. So I hope you understand three-dimensionally what's happening here, right? This is the gate, and the silicon carbide is actually compressed. The distance is, pulling it apart here.
Why do we not see that kind of fold on the
Because it's hidden behind this. If you rotate it, you can see it. Trust me on that. Okay? I'm not hiding it from you. It's there. It's just hidden. And yeah, so yeah, basically, just understand what I'm trying to say is that, the fin is being pulled apart in this direction, right?
Yeah.
This is the channel direction, and the gate is wrapping around it.
Why are there two gates?
Huh? Where's the second? What do you mean two gates? They forget that. That's just to show the pattern. Yeah. This is not an inverter. This is just a pattern. Yeah. I mean, if I showed everything, then there's no project, right? Yeah. So then, yeah. So everyone understands here, right? So I etch the nitride, open up the source drain regions, then wet etch the silicon, crystal etch, and then epitaxially grow the silicon carbide. Yeah.
Does it matter how much we grow the strains, or are we just saying, all right, we're going to strain?
For us, just grow it, but usually it's calculated how much you grow, because if you grow too much, it can even damage the device. So you grow enough to create the right amount of strain to give you the right mobility enhancement. Yeah. It will, but like it's okay. Yeah, but it will show you a difference.
Yeah, the targets.
Yeah. No, but you don't have IV targets for capacitance, right? Because usually this will only affect the. Oh, I understand what you're saying. No. The Covenant doesn't calculate strain induced mobility changes. Yeah. No way it can do that. Yeah. No, because this is silicon carbide, right? So depending on which, see, basically what you're doing is you are creating this, so this is the channel, right? And then say originally this region had silicon, correct? So originally this region was silicon, right? If I take the silicon and I replace it with something that occupies less volume than silicon, it's gonna obviously pull it, right? So it's gonna, if this was occupying less volume, it's gonna pull it this way, correct? So if I put silicon carbide, which has a lesser volume than silicon because it has less density, it's gonna have tensile stress. But silicon germanium is bigger, right? So it's actually gonna compress it. So it depends on which type you use. And it turns out that if you do compressive stress, it actually increases mobility of the holes. But if you do tensile stress, it increases mobility of the electron. Yeah.
We're talking about a spacer like 10 minutes ago. Where is that spacer?
This is the spacer.
So before we do any of this strain engineering stuff, deposit a spacer.
No. Remember, to create the lightly doped drain region.
Protecting that lightly doped.
Yeah, that's why this is there. This is the sidewall. Yeah. This sidewall spacer is here, and then that's why this protects you from opening the silicon where the lightly doped is there. So the lightly doped is sitting below the sidewall spacer, right? And then you open up this region and then you glue the silicon carbide. Not able to say if Zoom is still recording or not. I guess it is. Okay, then yeah. So everyone understood till this point, right? Why are you shaking your head?
I'm being honest.
Well, you can follow along the video. You can ask me later if you. Which part you don't understand? Okay, just watch the video. Yeah, but I hope everyone at least understands, somewhat how to do it. Yeah.
How did you like super selectively only wet etch that part?
No, because it's a silicon wet etch. It doesn't etch anything else. See, first what you did is you basically opened up this region, right? So you kind of see this is after silicon etch, but if you see before silicon etch, right? This is before silicon etch. So all I did was, so originally nitride was everywhere, right? Then when I dry etch, that's why the nitride here is gone. But you see the nitride on top of this is also gone, right? And it exposed the silicon. Now that the silicon is exposed, I do wet silicon etch, right? So the silicon is going to etch, but it's not going to etch anything else because everything else is covered with nitride and oxide, right? So the wet etch is only going to etch silicon. It's not going to etch oxides or nitride. So the silicon is etched down like this. That's why the silicon is now etched. Okay. And then, after this, then once you etch the silicon, then you grow the silicon carbide. Okay, so next what you do is, you gotta, so this completes the front end of it. Okay. Now is the middle of line. How do you create contacts to the source drain gate, right? So again, there's a lot of, actually it's not done. I haven't done the replacement metal. So let's quickly finish since we don't have much time. But so now I've created the source drain and the gate. So now remember there's polysilicon here, right? I need to replace this with basically a metal, right? Why you need to do that? Because I still haven't put my high K dielectric, right? Everything here is still like some oxide nitride, right? And once you put your high K dielectric, remember why you need a metal is because once you have your high K dielectric, you no longer can put polysilicon because polysilicon is a high temperature process. And the moment you do a high temperature process, when you put a high K, it's going to damage the high K. So when you have high K, it's always going to be, the next step is always going to be temperature limited. So it's always going to be low temperature process. Right?
Everything after the high K is low temperature.
Yeah, that's why I use a metal because metal can be deposited use CVD. CVD is a low temperature process. Sorry, PVD, yeah, sputter. Okay. So now what do you do? Now you do the replacement process, right? Remember, I was explaining to you, like, once you had this polysilicon and you had, your silicon germanium here. So what you're going to do now is you're going to basically, and remember there's a sidewall spacer here, you're going to basically put some kind of oxide and then you're going to CMP it down so that it's going to be something like this. Then what you're going to do is you're going to remove this polysilicon and replace it with the high K metal and then do a polish step. to fill in the hole, right, with metal. That's basically what you're going to do here. So first you're going to putting this oxide, and then you're CMPing it down, but remember there was a nitride on top, so it's going to stop on that nitride. And then what you do, you have to remove this poly, right? So you remove this nitride on top, so you etch it. And then what you do now, your polysilicon is exposed, right? So now you just remove the polysilicon. You can just etch the polysilicon, right? So now the polysilicon is removed. And then now you have this hole that is left, right? And now you can fill this hole with your high K dielectric and your metal gate, right? But here's where it gets a little complicated because you need to have different work function metals for the PMOS as well as the NMOS. Okay, so they're going to be different kind of, and we'll talk a little bit about that if we have time. But your NMOS is going to have a completely different metal for the gate, and the PMOS is going to have a different metal depending on work function, right? So now, basically, now you open up this, and now you need to fill it with high K, right? So you do an atomic layer deposition of high K dielectric, so aluminum oxide, hafnium oxide. So that basically covers everything. And then now, first you need to create the metal for the PMOS. Then you're going to create the metal for the NMOS, right? So remember, the PMOS is here, the NMOS is sorry. This is the NMOS, and the PMOS is here, right? So first, I'm going to create the gate for the PMOS, right? So the gate metal in this case is a combination of titanium nitride and tantalum nitride, and that really depends on what kind of work function is needed for the PMOS versus the NMOS. So first you sputter tinitride, tantalum nitride, and then remember that this metal covers everywhere, but you need to make sure that this P metal is only there for the PMOS and not there for the NMOS, right? So again, you need to remove it, right? So now you again do a mask. You put a mask here, and then you etch away the P metal so that there's no P metal on the NMOS, right? And then you remove the mask, and then you sputter again, but this is aluminum, which is for the NMOS. So this is N metal, right? So now you have P metal on the PMOS and N metal on the NMOS, right? And yeah. Yeah.
Again,
I'll go here. It's easier to explain to you.
no, I understand this. These are two different metals that make up P metal. Two different nitrides that make up.
Yeah, because they will actually alloy and give you the kind of work.
Sure. And then the next one we do resist. Then we do metal resist.
Then you put the N metal. You remove the metal from the NMOS region, and then you replace it with the N metal, right? See, that's what I'm doing here. So first the hafnia. This is the P metal.
Yes.
But I don't want the P metal on the NMOS region,
Yeah.
right? So I remove it, right? So I mask it, and then I etch the P metal here. So it's gone. Just wet etch or something, dry etch or wet etch. But it stops on hafnia. But always, when you etch, it's one versus the other, right? So this etch can etch a metal, but it cannot etch an oxide. So it stops on the hafnia, right? And then now you see the P metal is only on the PMOS. There's nothing on the NMOS. But now when you sputter aluminum, which is for the NMOS, so aluminum now sets the work function of the NMOS, right? And the PMOS has its own work function. It doesn't really matter that the N metal is sitting on the P metal because it's only the metal that's nearest to the gate oxide that determines the work function. So this other metal which is sitting on top of the P metal, the N metal on top of the P metal, it's just a conductor. It doesn't really contribute to the work function. Okay, it's only the metal that's in contact with the hafnia that matters. So that's why it's okay that this N metal is now. It's okay that this N metal is sitting on top of the P, right? And now you have defined basically your hafnia. You have defined your actual metals that defines the work function for the PMOS and NMOS. And now you still have this empty space which you need to fill with some conductor, right? So that's typically tungsten is used for that. So you sputter tungsten, so it fills everything. And then to finally fill the holes, you do a CMP. And the CMP is going to stop on the it's a time CMP again, okay? So it doesn't stop on a nitride but you time it so that it just gives you the gate height that you want. Yeah. I'll talk about that if you have time. Yeah, it depends on, it actually depends on semiconductor physics, which I'll briefly explain.
It's only the one that's contacting the channel that works, then why do we need 2 layers of metal for the?
Because it actually alloys. One metal doesn't give you the work function.
Then will this N metal alloy with the P metal?
No, it won't actually. Yeah, but so, yeah.
The gate, we don't have any metallic contact in semiconductor. Why do we care about the work function?
For the gate, you know, what do you mean?
This gate, the metal touches the semiconductor through the oxide.
No, yeah, there's a hafnium oxide between the semiconductor. Metal doesn't touch the semiconductor.
Because of that layer, the metal doesn't directly touch the semiconductor.
Most cap.
It's a capacitor actually.
No matter, right? For most cap.
See, when you make the transistor, right, there's always this oxide between the gate and the silicon.
We care about the work function to determine the bandwidth, right?
Yeah.
But my question is, now the metal is not touching the semiconductor.
No, you're talking about Schottky or ohmic contact. That's different. This is a MOS capacitor. You're creating a capacitor here, but the threshold voltage really depends on what is the work function difference between this metal and this semiconductor. Which I will show. I do have it. If we have time and if you guys have time, I can show that. Okay. Yeah, so you have the, just to repeat, N metal, P metal, and then you fill everything up with tungsten, and then you do a CMP, but this is a reference CMP, okay? You CMP till you get the gate height you want, right? So now I did the CMP, and then after that, you usually cap it with some nitride, okay? So you deposit some nitride, and then you cap the surface with nitride. Usually this is an additional step that is used. You always don't want to expose the gate to the elements. So you usually cap it with nitride.
How did you CMP the tungsten down to so deep side?
How did I see? Oh, because tungsten is like, you can CMP tungsten. Yeah, compared to nitride, it's soft.
We had like a very high stack, right? But in this case, our tungsten is like dished way lower than oxide. Right, can we go backwards? Is this black right now, the tungsten, right?
Yeah.
How?
No, there is a nitride here, by the way. It's below that.
Oh yeah, this overall. How did we get that?
No, actually, you know what? I think when I did the simulation, right? I think I didn't give, this should also dish out. Okay. But, it's not really that critical. So you don't need to do it if you want. So, but once you have this, right? So the main thing is now this completes the front end of line process, right? Now you create the contacts to your source and drain, correct? So now to create contacts, it's just the same as the previous case I mentioned earlier is, once you have this, once you have the gate, this is a replacement gate, right? So this is now metal. Now what you do is you just fill it with some kind of oxide, and then you planarize the surface, and then you etch down contacts all the way down, and then you fill it with tinitrate tungsten, right? So that's your tungsten contact. So that's what I'm going to do here. So yeah.
What is that like darker light here that we put after the cap, after the nitrate?
This is just some oxide. Yeah. So that's what, it's just some oxide that I planarized with CMP.
It's the material that's on tungsten?
That's nitride. It's a nitride capping layer, actually.
When we etch down to make our contacts, is there any rule that we have to use to try to figure out the sizing of the mask that we use to make the contact?
That's in the design rule usually. So usually the design rule will tell you what the contact size is for, so if the polysilicon is like some size, so polysilicon is some size, the contact has to have some distance from the edges or something. That rule will be there in the design rules. Yeah, and so, now you create your contact. So you put, again, 3-layer resist, you pattern. So this is the contact to the source drain. This is the contact to the gate. And then you etch down all the way till the, basically the metal. And that's what's shown here on the right. And then what you do, you fill it with, you basically sputter tinitride tungsten. So tinitride is usually a barrier. You always don't want to put metal directly in contact with silicon. So you put some tinitride and then tungsten, and then you CMP it down, right? Again, this is also a reference CMP. So the CMP, where you stop, depends on how long you do the CMP, and you have to optimize that. And then now and this completes your complete front end of line and middle of line, right? So now you've created your tungsten contacts to the FinFET transistors with the replacement.
You said this is a timed CMP?
Yeah.
But you are showing it polished stop.
No, there's no polystop here. Everything here is oxide. No, there's no polystop. See, this is oxide, this is
Okay.
tungsten,
Yeah,
this is tinitride. There's no nitride here.
yeah, but it stop at oxide, right?
No, there's no stop. You basically put enough height, so you put enough height of oxide,
Okay.
enough height of tungsten, and then you CMP all the way down and you stop.
You also remove a nitride, high nitride.
No, tinitride is not a polystop. Tinitride is just a
You
barrier.
remove it, right?
Yeah, you remove it. That's what I'm saying.
Where did I remove it?
After your CMP,
Yeah.
Oh, but that's timed.
That's
It's not stopping on the oxide.
you're over it.
Yeah, you're
Oh, I
polishing
see.
till it goes
Oh, I
away.
see.
You understand what I'm saying?
You're also polishing oxide at that time.
Yeah, oxide is just soft. You're just polishing. Okay. See, no, you are asking, did I stop? No, I didn't stop on this oxide. It's not a polish stop. It's a timed CM.
Okay.
I'm polishing the oxide also, actually.
Okay.
Yeah, so that completes the structure, and you can see, how this looks like once you made everything kind of transparent. Is this is your your actual source drain. This was the contacts, and this is your replacement metal gate, right? Which is going, and you can see here how this is the channel, and the gate is actually going like this one. And this is your entire thing, right?
So the CD or silicon carbide, it's not only your material for strand, it's also your source and drain.
It's also your
Source and drain.
yeah.
Okay.
Yeah, that is your source and drain.
Yeah, I actually moved this question.
So two things I haven't included here that I expect you guys to include is one, I haven't done silicidation. You have to do silicidation on the source and drain, right? That's one I haven't shown. The other one is a lightly doped, but that's that's just an implant and edges. So that's two things I haven't shown here.
How many steps do you have?
I didn't count. Just leave it at that. So this is the the final structure. And after this, it's the job is not done, right? Because you have an inverter, so you still have to connect the transistors together, right? So then you do the back end of line. So back end of line, that's not that difficult. You just put oxide, you create a pattern, then you basically put a seed layer, electroplate copper, CMP, and then you create metal 1, then you create dual damascene, then to create metal 2, right? Then that completes your thing. So on top of this is just the front end, middle end, and then on top you'll have 2 levels of copper that defines your back end of line, right? And then you have the full interconnected transistors, right? And so here's an example of a 14 nanometer cross section. So you can see here, these are the fins, right? You see they're standing up here, and you have around 13 levels of metallization to go all the way to the top of the chip. Okay. So, and if you notice here, right? So, yeah, so basically these are the vias, and these are the actual metals that are, created using. And the reason why these metals are, you see they are very flat on the surface is because there's a CMP step here. That's why they are like flat. And you build on top of
Looks like on the higher level, there's another layer.
it. What do you mean?
Cells.
Is it different than like there's no this?
Oh, actually, I don't know what that is. There could be some these are all but it's a dielectric for sure. It's some dielectric. Probably they're using some nitride oxide something. Yeah. So, so usually, right? So this is just something I added in. Is there was a question that Rehan asked as to how do you physically measure? So when you do the lightly doped drain region, right? How do you know that's the profile you get in practice, right? So there is actually a way that you can actually physically see what the source drain regions look like, and there's a technique called as basically scanning spreading resistance microscopy. Okay. And if you guys know a little bit know what an AFM is, it's basically an atomic force microscope, but it does electrical measurements as it is scanning the surface, right? So it's measuring basically the amount of resistivity at the surface as it's scanning the surface, right? So here's an example of a plot created for an actual transistor, and you can see how the conductivity is varying. And you can see clearly here the lightly doped region, right? So in practice, this is how they actually physically measure and see and confirm that the implants and the diffusion gives them the profile that they want. Okay. So you can physically see what the profile looks like. And here's like a typical scan. You can see the distribution of the dopants, the conductivity. And the reason I included this is because you want to match this as close to this as possible. This is what you would get in a FinFET. So this is the same kind of procedure done on a FinFET. And you can see how this is the gate, and you see it's highly conductive. And you see how the distribution of the dopants in the fin is almost uniform, right? So this is when you do your well doping, so this is the kind of thing you want to target. You want this kind of doping profile.
This thing is 200 nanometer high.
Yeah.
I see.
But this is the whole fin, it's not just the,
Oh, I see.
yeah.
Do we have this to at UCLA?
I mean,
I
I don't think.
That need to be done.
I mean, you can convert an AFM to this, I think. Yeah. This is just an AFM, but it's an AFM that has basically it's like coated with metal. So it can also do like, you can pass an electric current and measure the conductivity. Huh? As in? Yeah. It's a scanning, yeah, exactly.
When we use that in the circuit, how do we control the bulk voltage?
Oh, so actually I talked with professors, don't worry about the bulk, what do you say, the bulk contact. Just care about source drain gate, because then it gets very complicated. Yeah, you need,
Practice
there's a body contact. Yeah, obviously, yeah. There will be a body contact.
Question regarding ion implant. So for the doping, do we have to use the deposition annealing method, or we could do MBE or ion implantation?
You can do any step. You can do diffusion, you can do ion implantation, or you can, the way I showed it is you can use a poly to dope it. There's like many ways to do it.
How do we control the ID sets of PMOS and NMOS?
How do you control ID sat? So that really depends on like the mobility and the width of the transistor, right? Oh, you mean the intrinsic ID sat?
How do we control the width of them?
Usually what you do is if you want the NMOS, so usually in modern technology, right? The strain engineering, all that is done in a way that the NMOS is as close matched to the PMOS as possible. So so the number of fins on the NMOS and the PMOS is approximately the same. But if you had a situation where the NMOS has a higher mobility than the PMOS, right? Then you just add more fins to the PMOS to match the current, because you want same current in the NMOS and the PMOS.
It looks like when we want to add more fins, like double it.
Yeah, it's great. It's not complicated. It's not like planar. You can only have one.
That's
two,
true,
three.
yes. Also, the side fins are not used usually. You only use the central fins. Yeah. So, so this part of it, I am allowed to upload. So I will upload this part. But again, I don't think I have time to go through this, but definitely, the main thing to understand here is that, you guys can read this up anywhere online. It's on basic transistor physics. It's like, so you have some kind of band structure on the gate, the oxide, and the silicon. And when you put all of them together, right? So what happens is you get some kind of a band bending, and you get some kind of a structure, okay? And I don't really have time to go through this, but I think the main important point to understand is, if you take in basic transistor physics, is that based on how, what metal you choose and the doping of your silicon, you can actually have formula to calculate what the threshold voltage is, okay? And the important thing to understand is that usually the threshold voltage is going to be the work function difference between your gate metal and the silicon. And also there's going to be this term, which is actually the amount of charge in the silicon over the oxide capacitance per unit area, okay? And over here, you see this Na, right? So depending on how much doping you have in your body, as well as the work function difference, you can calculate what the threshold voltage of the transistor is, right? In a FinFET, is slightly complicated, because in your case, right, if you assume that the fin is not very narrow, then you can assume that you can assume that there's not much variation in the potential when you go in the orthonormal direction. Okay, so this vector is normal to the fin, right? Normal to the surface here, right? So this is the gate, this is the actual silicon, and this is your inversion layer shown here, right? So if the potential is not really affected in the cross section and only depends on the normal direction, right? Then you can use the same formula I showed before, okay? Because you're just calculating in the normal direction. But if your fin was very narrow, right? Then the way usually people do it is you need to actually calculate. You need to solve Poisson's equation in this cross section, calculate what your potential distribution is, and then from that you need to calculate what is the total charge in this and divide that by Cox to calculate your threshold, right? And this can get very, very complicated. So here's an example of how it is done from paper where they solve the three-dimensional Poisson's equation in the cross section. And so the charge, when you solve this, the charge calculation for the potential distribution gets very complicated. And so here you see this is the potential as a function of location within the
Analytical solution.
Yeah, this is an analytical solution. But then, I just wanted to show that, how you would do this in the FinFET case. But then for our case, right, you assume that the FinFET is not that narrow. So you don't have to do this two-dimensional Poisson calculation. And you can assume that the potential only varies in a normal direction. So you can use this traditional bulk mass formula. Right? He's very happy. Yeah, so, and here's a summary of different kinds of metals. So depending on whether it's a PMOS or NMOS, when you use that formula, right, it turns out that only certain metals work to give you the correct threshold value for a PMOS versus an NMOS. And usually for all the possible metals, right? So you see for the PMOS, typically that's why we use a kind of titanium or something like that. Yeah.
So here you're showing work function of metals, but we do all the depositions, all the nitrides. Why do we do that? Why is it
Because that actually changes the work function slightly.
well, we nitride every.
See, the metallurgy, usually when you deposit these things and you anneal it, right? A lot of metallurgical things happen. They alloy and all that stuff, right? That gets very complicated. For your case, you can just use a metal, that's fine.
Okay.
Yeah. But just, so these are like examples for the PMOS, right? So that's why typically PMOS will be some kind of titanium-based thing. And NMOS will typically be some kind of aluminum-based thing. That's why you use aluminum for the NMOS, right? But you use titanium for the PMOS, because that's what gives you the right work function. And usually, there's a lot of physics that goes into choosing the correct kind of metal and correct kind of alloy. And you use a lot of, that's why, when people usually design a transistor, there's a whole team that models this using some kind of CAD software to model how the potential is in the cross section to calculate what the threshold voltage is. And then they choose the metal that gives you the right value of the threshold, right? And that usually involves some kind of alloying and different kinds of metals are used. Yeah, so that's.
In the Proventor and in my material lab, in my material library, all the work function of the metal is the same. It's 4.6.
You have to change that. Yeah. All right. Yeah. You have to put the right work function. So when you're doing this project, right, you can just assume something like titanium. You can substitute the work function, calculate what the doping is. Yeah.
Thank you.
Right.
Without this, I would just flounder.
Yeah, I will upload this video so you can you can follow with the process. And yeah.
So when the first time we built the fin, is it for the well or for the LED?
Seems like it's possible.
Huh?
The first time we built